Okay, welcome everyone. I'm pleased to introduce Simon Dürr. He will be presenting deploying machine learning models for proteins on the web. Simon is a PhD student at EPFL. He obtained his master's and bachelor's of science at the University of Constance. His research interests are in computational enzyme design with machine learning, QM/MM simulations, and evolutionary algorithms. Simon.
So thank you so much for being here. I'm very happy to talk to you today about how to deploy protein machine learning models on the web. And as you can see from this title slide, so I'm going to be covering Google Colab, but we're also going to talk about Hugging Face, about Gradio, and also about Streamlit. Just a quick disclaimer before we start. So I'm a member of this Hugging Face Fellow program. I don't get money from them, but sometimes they give me like stickers and stuff. So if you ever meet me in real life, then I'd be happy to give you a sticker. But apart from that, I don't get any financial compensation for speaking about Hugging Face. And I will also in this talk not only to speak about Hugging Face products, but also about other stuff. Okay, so if you've been doing protein machine learning, then probably this cartoon is quite close to the experience you lived in the last months, right? So there's a lot of new papers coming out, and it's quite challenging to stay on top of the literature. And it would be quite cool, right, if we could easily test what new papers kind of do if there would be demos. And this is kind of useful because then you could just review the capabilities of the models. You could really see does the protein structure that the model generates, does it look realistic, for example? Also, if you want to build on this stuff or if you want to compare and benchmark, then if you have a demo available, you can very quickly do this. And it's also pretty easy to learn and get inspired. And if you look at what most traditional journals do, then nowadays they have these like policies for open data and code. But if you look at the protein ML field, a lot of people publish preprints or just in conferences, and it's pretty much a Wild West. So there is no good standards of what to publish, when to publish it, and so on. And we've really seen this, for example, with these protein diffusion models. There's a few papers that came out in very rapid succession, but most of them didn't have code available. They still don't. And it's really hard to kind of make sure to know what the models do if you don't have the code available, because you can reinvent it or you can kind of use the description in the text to kind of try to reprogram it, but it's kind of hard and also takes a lot of time. So it would be quite a lot easier if people would put code online. So I guess, therefore, most people would agree that it's quite would be quite useful to share such demos more widely. So if you then kind of decide, okay, I want to do this, then you may be like this guy. So yeah, you want to show off your model using a web app. But then once you look into details, it gets quite hairy quite quickly, right? So you have to learn all these different tools. So your experience will be, you will have a lot of frustration doing this. And kind of if you look back, maybe 5 to 10 years ago, right? So if people were building such demos, then yeah, you train your model using a framework of your choice, but then you have to kind of go through these additional steps of kind of containerizing, deploying a model, for example, using a Docker image or using AWS infrastructure. You have to kind of have some way of storing incoming samples, and you also have to know kind of how to do front-end development. So build like a web page that people can easily access. And so people have been doing this, but I'd say it's, if you look at the long-term sustainability, it's not super successful. So this is some examples from literature research for one of my own projects, right? So I was looking up web servers that were developed in 2010, and if you go to them, like the URLs that people put in the papers, if you click on them, then you see these like four error messages, not found, or site can't be reached. Some pages also just look terrible. It's not a real well example, but I think there are some sites that really look a little bit like this. And then also if you view it in terms of, say, privacy or GDPR compliance, most researchers don't know anything about this, and it shows. So really kind of scientists are probably not very good web developers, and also they shouldn't be, right? Because it takes time to learn this skill, and you always spend a lot of time doing research. So this is something that you don't want to do. And this kind of new way of building demos is, again, you build your model using framework of your choice, but then you have all these steps 2, 3, and 4 that are in the same framework. For example, there's this Gradio framework built by Hugging Face. people have also been using these Google Colab notebook. And there's also this library called Streamlit, developed by a different company. As you can see, so most of this you can do within Python, so you barely have to know any web development to do this. And if you look more generally, kind of what are requirements that you would have for such a platform to share demos, then we would want something that is open source and doesn't depend on the company. So it should really be independent. Then also we want something that is agnostic of the problem that we're looking at. So should not make opinionated choices about anything, so that you have really free-handed designing your demo as you want it. We also really want this containerization. So we want that we can specify the complete environment being used for our model inside our app, so that if people use it in 10 years from now, they still know what kind of packages we installed and what versions they are. This kind of is in the broader context of this kind of fair terminology. So we want our model to be findable, it should be accessible, should be interoperable. And that means that it's not only humans that should be able to kind of fill out the form, click on run and get the predictions, but it should also be possible for a computer. So it should be able to make API requests to your model and get your output. And then all of that kind of also makes your model reproducible. So people evaluating your code will be able to check what you're doing pretty easily. And ideally, we want all of this, but with minimal effort. So we just want the wrapper that we can wrap our normal code that we would otherwise just put on GitHub, so that we have kind of readable code that people can easily adapt, but at the same time, we have this nice web app that people can interact with pretty easily. If you look at Google Colab, so people have put up quite a few notebooks using Colab now, and I guess one of the main benefits is that you get this free GPU, and that Google Colab is basically just a glorified Jupyter Notebook. Glorified in a sense that this is all Jupyter Notebooks, but you can kind of create these simple web forms using Markdown, and with that kind of people can put in a protein sequence, and they don't have to see the underlying code directly, but they can very easily show it. And another advantage is that, so if you share a Google Colab notebook, people click on it, then they will get their own copy. So basically, you don't have shared resources for the users, but each user can use their own GPU and run their own predictions, which is quite nice if you want to modify something, or if you have something that's quite resource hungry. On the downside is that in Google Colab, it's very hard to define the environment that you're running in, because so you can install packages in there. You can also fix the versions of those packages. But for example, the underlying Python version, that one is defined by Google. So if Google makes an update to the Colab environment, then all of the notebooks will have that new Python version. So you don't really know, like in 5 years from now, will it still run, because you have no control over parts of the environment. Also, this Markdown-based form editing is quite limited. So if you see, for example, here, this file upload component is unstyled. So it's pretty boring and it's hard to use. And you can also not use Colab notebooks within other environments. So you really have to stick to Google's platform. You cannot embed them as iframe, for example, somewhere. And this Pro that I put, that is just a glorified Jupyter Notebook, that can also be a bad thing. Jupyter Notebooks are quite known for kind of enforcing bad software engineering habits. So really, you put all the code in one big notebook instead of kind of writing a nice modular library that's more easy to reuse. A pretty popular example of using Colab to share a machine learning model for proteins is this Colab Fold that I guess most people here have used. You can see this UI that's you can very easily build using Markdown, but I know that kind of this requires a bit of maintenance. So every once in a while, the maintainers, they have to check that kind of the environment Google is still the same, that it still runs. So it's not the best. If you look at other UI libraries that are available, there's this Streamlit library developed by a company that kind of does things a bit better, because there you have this multi-page implementation that you can use. You have this custom component library. You have a lot more flexibility in how you set up your model, and you can host your app on GitHub, or you can host them in multi-page spaces, and they even run locally. And if you want to run in Colab, you can, but it's a bit hacky. And the main advantage is that now you use this requirements file to really define what kind of packages and what version of them should be available to your app. So with this, you ensure that you can rerun it. On the negative side is that Streamlit, same as Google Colab, doesn't have an API that you can carry, and it's a shared resource. So you will launch your app will run on some server in the internet, and all the users connect to that same app. So if you have something that uses a lot of resources, then all of the users have to share that resource. A cool example here is, for example, this Rust Score app built in Roland Dunberg's lab. So you can check it out. It's basically an interactive exploration of this Rust protein family, and you have these nice protein visualizations using high 3D mode. If we go to the next library, this is Gradio that is developed by Hugging Face. You can run it on their Spaces infrastructure, but you can also run it anywhere else. And on the pro side for this library is that you have this also very flexible API to kind of build complex multi-step interfaces where you really can define a workflow that people have to go through to develop it. And you also have plenty of UI components available that, for example, here, you can play Pictionary, so people can draw something and then you can output the predictions like it's described here. Same as for Streamlit, you define your environment using these requirements files, and you don't really know, you don't need to know what, for example, Docker is, because that's all done behind the scenes. And you really just define what packages you want to use. The cool thing about Gradio as well is that it's, so you can run it locally, you can run it hosted on Hugging Face Spaces, for example, or on your own servers, and it also runs within Google Colab notebooks. So you can kind of develop your UI, and if you really need a GPU, you can still have people run it in your Google Colab notebook. Also, you get this free REST API. So basically, your app is not only accessible from a web browser, but people can also just send requests to your app using Python and then get the predictions output from there. On the negative side is that there's a bit more separation between code and the UI than there is, for example, in Google Colab. So you have your code and the UI hosted on Hugging Face Spaces, but people only interact with the user interface. And if they want to see the code, they have to specifically go to the Git directory and kind of check the entry point of your app and then kind of go from there to see what's happening. Also, it's, again, a shared resource, so all the users share the same computer time. And for example, if something goes wrong, then the logs are only available to the owner of the space where it's hosted. And it's not that easy for users to kind of know why their input is failing. Some examples that I have built or other people have built are, for example, this Protein MPNN web app. So here you can use Protein MPNN to take a backbone, get a new sequence for it, and then refold those sequences using AlphaFold, and afterwards you can compare how the old backbone compares to the new structure that's predicted based on the sequence that the model designed. If you look at the Hugging Face website in a more global perspective, then so you have this Spaces part of the website is for hosting demos, but on Hugging Face you can also host models or data sets. So with models is just the model weights and some small wrapper that you can call to do inference with the model, but it's not a full-fledged demo where you can kind of have example inputs and these kind of things. Data sets, as the name says, for data sets. If you host your app on Hugging Face Spaces, by default, you'll just get 2 CPUs and 6 GB of RAM for free. So this is free forever. Your app will go into hibernation if it's not used for some time, but apart from that, that's pretty great. And if you want more, then you can also upgrade to GPUs, for example, or to smaller, bigger GPUs. And they also have this community grant functionality. So if you have something cool that you think is nice and you want to show it off, but it needs a GPU, then you can apply for these GPU grants. And since I have this fellow position, I might be able to speed things up for you. So if you want to do this, then just feel free to ping me, and we'll see what we can do. As I mentioned, you can host these Gradio apps locally, but the nice thing is that they also give you like a global URL. So I can, on my workstation, launch a Gradio app, Then I get an URL that I can share with anyone on the internet, and then they can run predictions on my workstation, which is quite nifty if you're quickly showing off something to colleagues, or if you want to run your predictions on a cluster, but you want to kind of quickly play around with them in your laptop on your local machine, then you can very easily do this. And the share URL, so that's the local URL, but then you also get the share URL that looks a little bit like this. As I mentioned, you have this free REST API. So if you go to a Gradio app that has built with a new version of Gradio, then you see this use via API button, and that will give you just an automatic API documentation. So for example, here, if I want to get a prediction from protein MPNN using Python, I can just import a request library and post the request to that URL, and then I will get back the designed sequences from the model. So it's pretty easy, and you don't have to do anything extra for this. You might wonder, why is this nice? And this is pretty cool. For example, I've seen this when Meta AI launched ESM-Fold, because they also had an API. And with the ESM-Fold API, people very quickly built this Chimera X add-on. So in Chimera X, you can just open the PDB file and then call the ESM-Fold API to predict the sequence for that PDB file again, so then you can compare the predicted and the model that you uploaded. And if you have a REST API for more models, then you can really do this on a much more global scale. And I think there's a lot of possibilities for people to kind of use your model in some other tool that might be useful, for example, for experimentalists. If we talk about protein ML, then often you would want to look at protein structures, right? So structure is a 3D object, and it's very hard to look at it from a picture in a paper. Like, does that protein look realistic or not, or do the sidechain angles look good or something? So the cool thing about doing this with web-based demos is that you can actually show off your protein structure, or the protein structure that your model is designing, in the web browser. There's a few different libraries that you can choose from. So for example, there's this NGL.js library that also has a pip installable package. There's 3D Mode.js, and then there's also this Moldstar viewer, which is now the default viewer at the RCSP Project Data Bank. Moldstar is pretty powerful, but doesn't come with a Python package and is a bit more difficult to set up. So probably don't want to use this for now. And 3D Mode.js is what I would recommend, what I've also used for most of the apps that I built, just because it doesn't have any dependencies now. It comes with a Streamlit extension, so if you want to use it in Streamlit, you can use this STMO package, and with Gradio you can directly use it in the Gradio app. And it supports most of the stuff that you will also use. For example, from PyMos, you can show protein surfaces, you can show cartoon representation, you can show different things. You can even have these little hover icons to highlight something in your structure. So it's really powerful, and you can very, very easily adapt this to what you need. I should mention that all of these libraries, they're developed by scientists, so it's not a company that develops them. So if you're a scientist and you use them, then you should also cite them in your papers, because that motivates the developers to kind of continue working on them. If you look at Gradio, then there's quite a flock of components that is available for you to use. So you can use text boxes and checkboxes and dropdowns and so on. So you can just take a look at the documentation, but the real power is this HTML button. So if you want to implement something custom, you can very easily do this with this HTML component. Now you might wonder, so if I build something like this, how can I cite it, or how can other people cite it? So for now, what you have to do is just put it on Zenodo, and you get a DOI, and you can put that in your paper, and people can cite it. Hugging Face might add DOIs to spaces as well. So at the moment, they support citing models and data sets using the DOI, but I've opened an issue with them that it should probably also allow this functionality for spaces. So if you're also curious to do this, then be happy if you chime in here and really listen to feedback. So that would be nice. And this is a very new feature on Hugging Face, that they also have these paper pages. So you can basically claim a paper using an archive identifier, and then you can see what kind of demos and what data sets or what models this paper refers to that are available on the Hugging Face hub. If you're looking for demos to get inspired or kind of see what other people have done, I also built this website, which is called colabdb.github.io. So here you can browse some other models people have put online, and you can also comment them. The code and everything is available there, so you can check, and you can also submit. So if you have a cool notebook that you found, you can submit it here. And kind of the goal is to build a collection of notebooks that, or of notebooks and demos that are useful to people that are working in this space of protein ML or chemistry and machine learning. Okay, I think that's enough talking. Now I'm going to try doing a short little live demo of how this works. So just bear with me while I'm changing screens. So the goal is to build a small app that, given a protein structure, will use DSSP to kind of highlight the secondary structure coloring. So just let me share my screen and go to the Hugging Face website. So that's where we'll start. So if you create a new space, then you just go to Hugging Face, you click on your user icon, and you can go to new space. So here I'm just going to do protein ML demo, DSSP, for example. You can choose a license. So I'm just going to use MIT license. And then here you can see already that you can host Streamlit apps, you can host Gradio apps, you can even host Docker apps on Hugging Face. You can just also use static websites and choose Gradio, and use the default free hardware, and you can select the other things that you'll be charged for. So just create a space, and then you can see this is just a Git repository. So I can now go to my code editor, just change my screen. Okay. So is this? Okay. So I guess you should see my terminal now in VS Code. So I can just clone the space that I just created. See, it's just a normal Git repository. I have this README file in here that you can check. So if I check this README file, then here you'll see what SDK version you're using. You can also put some information on how your space is working, or install instructions, or what packages you use, or citation of your paper, and you can add some other configuration options. Now, first, as that, we need to create this requirements file to kind of tell Hugging Face what kind of packages it should install. And here we're going to use Torch. We're going to use the Gradio library. We're going to use this py3dmol package that I just mentioned to show off our protein structure, and we'll use this Torch implementation of DSSP so this is hosted on GitHub. It has a setup py file in it. So using pip install, you can just install it like this. So basically what this requirements file will do is we will pip install Torch, we'll pip install Gradio, and so on. Okay, so that's all sorted for our requirements. Now we can create a file which we call app.py. So this is basically our entry point. If you go to the README, you can see this is the app file that is written here in line 8. So basically, when Hugging Face launches your space, that's the Python file that will be used to render your app. Now here we just we import the Gradio library, and then can we first do a quick demo of how to build such an interface. So you use this Gradio blocks API like this. So you just use this with block, and then within the with block you can do demo launch. And then in here you have all of your here in this with block that's where you set up your the form elements that you want to use. So here, for example, I want text input. So I use gr text box, label PDB code, and I want a button called BTN. So it's radio button with label run, and I want something where output my stuff using gr HTML like this. And so we can try launching this. I've installed that same environment here on my local machine under radio proteins. And so you can see here, I'm again in my folder where I have my app file. I can launch my app. I just type -app.py. This should launch my app. And here you can see this running on my local URL. I can easily show this directly in VS Code. If I use this simple browser, I can just copy that URL. And now you should see, so now you have your app on the right side and your Python code on the left side. And you can see it just did what we told it to do. So we have a text box that has label PDB code. We have our run function, and then the HTML output is currently not visible. So, but now kind of if I click, nothing happens, because now we need to kind of add some logic here. And we basically do this if we by adding an end listener here to our button. So just call button click, and then I specify what function I want to run if I click the button and what inputs and outputs I'm using. So the input should be PDB ID, and as outputs, we want to have our HTML box. So now you can see it's complaining my run function not defined. I'm just going to quickly define it. Define run. Here I'm going to take PDB ID as input. And then as a first demo, we can just quickly do return. And you can turn a string of the PDB ID just to show you that it works. I click on save. And now I'm going to, so I have to cancel the currently running app and restart it. And the Gradio people even made a live reload functionality. So if you instead of calling Python, you can do Gradio app.py, and this should automatically reload the app whenever you save it. So I see it's launching in reload mode. HTML is not defined. The event listener at the wrong location. So see, I saved and it's reloading. So now everything is working correctly. I refresh my page here, and if I add test hello proteins, and I click on run, this shows up here in the HTML output. Okay, so let's build our actual app where we need to have some more packages. So we will import the py3demo package. We'll import Torch. We'll import PyDSSP, and we also need the OS package. So let's first complete our UI. So I also want something where people can upload a PDB file, because some people might want to just show off their, might upload a local file. So this is very easily accomplished as well, a gr file. Here you can set label PDB file. Then I want something where people can select colors. So if they click on run, then it will compute the secondary structure assignment, but then I kind of want the users to give the ability to kind of color it as they want. So with this, we can try another function to quickly lay out stuff. So with Gradio, you have the option, for example, to use gr row. There's also gr tab to make like a tab interface, and other possibilities that you can check in documentation. So basically here, I'm going to create this row, and then I'm going to have 3 color pickers. So just create a color picker like this. Called Helix, and then I'm going to do the same sheets. loop. So modify this here at the beginning, loop, sheet, and change my click function here so that run not only receives the PDB ID, but also receives the other inputs that I just specified. So build sheet loop, and save this, and then we should reload, and we should see that we have now our PDB code, we have our PDB file. So if I click here, I can upload the PDB file, and here you can also select colors, but still, so nothing is happening because at the moment our app just gives you just output a text input. So first thing we need to do next is kind of get all these attributes also to our run function. So now you see we have PDB ID, PDB file, helix sheet, and loop. And basically in run, we can do all our logic now. So this is all the code you need to generate this interface and nothing else. And you can even see, so down here, you already have this used via API thing. If I click on it, then if it's hosted on Hugging Face, then you will see the documentation of what's happening. Okay, so I said we want to visualize our the secondary structure assignment. So for this, we just use a function that I already predefined. So basically, this will take as input the PDB code and the file path. And for file path is defined, we'll use a local file. And if not, it will try loading the PDB file from the internet. So I just call this variable path to PDB, and then use this get PDB function where I say PDB code is the PDB input from the PDB ID field, and file path is the PDB file. Now, with this, I can now read the file because it will be available locally within the environment. So I just use the -open function to read in my PDB file. And if I compute the secondary structure assignment, then it's always zero-based. Some PDB files might have different indexing, so I need to do something to correct this. I also prepare a small function to do this. To call get offset. It's also just a very standard Python function. Put here, and then we will run our model. So this PyDSSP program, where you very simply have 2 lines of text. So here we'll put the content of our PDB file. So basically, we'll use this helper routine in the package, read out the coordinates, and then assign them using the function in the package. And then you have your secondary structure assignment in this. You can also quickly visualize this. Instead of our file name, just put this here. So just save this, reload our app. Just need to quickly wait. Now click on reload. You can put PDB code, for example, 1QoS, and click on run. And then you can see, okay, it's provided me the secondary structure assignment with sheets, helices, and loops denoted by different letters. Okay, so now this is pretty boring. We want to visualize it on the protein. So here you can just use Py3DMO. There's a Python API for it, which is in this Py3DMO package. So first, just create the viewer object. Then you can add your model using the add model function. So here I'm just taking the string that contains the PDB content and telling Py3DMO this is a PDB file. You can also load XYZ files or other stuff. Then I create a color map. So at the beginning, we can use a color map that is defined with fixed values. So just helix should be this color, loops should be this color, and sheets should be this color. And we just need to tell Py3DMO to color our stuff like this. And for this, we can create a map that maps each residue to the secondary structure assignment. So this is just this function where I say for residue I plus the offset, take the value from the color map, and I just iterate over the secondary structure assignment that I just computed. And then the only thing I have to do is to tell P5 3D model to kind of apply that style to your molecule. So you just use the set style function, saying, okay, I want cartoon style, and you should use the color scheme that is residue based using the color map I just defined. So it's a little bigger, you should see it. And then as a last step, we will also tell Py3D mode to kind of center the view on the structure that we're inputting. And the only thing left to do is to output the actual HTML. For this, Py3D mode has this helper function. So if you have view, then you can call _ make HTML. It will give you the HTML content that needs to be rendered by the browser to visualize the structure. But so that's a little catch. You need to do some extra work because the way how we're embedding is using an iframe. And here you can't have single quotes. So you just need to replace all the single quotes with double quotes. And then also this does not work directly because of the security measures that I mentioned. So you can just use this predefined code that, so I will share the code of this demo with you. Just use that predefined code that I'm putting here. So basically this will create an HTML document within the HTML document and then output it. So if I save this and run the model again, then it should already give us our front-end instruction. So let's finish building, reload, type 1 QS, click on run, and then voila, we have our plotting structure. And it's the colors that I just defined. If I want the users to be able to choose based on the color maps, I just need to replace here in the color map, instead of the fixed values, I just use helix, loop, and sheet, so just the inputs that come from the form. Like this. If I save it and reload it, then I can put again the same protein, and now I can define the colors. So I want helix in red, I want sheets in blue, and I want loops in green. Click on run, then that's exactly what's happening. And if I change it, so if I want the loops in say pink, click on run, and then loops are in pink. So it's very, very easy to modify this, and you can, based on all the input fields that are available, you can really make all kinds of interfaces that you want. Now, maybe a last example. So often if you make a demo like this, it's useful that you have some kind of sample input. And using this Gradio app, you can also very easily do this. For this, we just go back to our UI block down here. So you just there's this examples function. So you can just do gr examples. In here, you just create a list of the examples that you want to provide, and in each, so this is a list within a list, and in that list you provide the default inputs for the different fields that you want to pre-populate. So here, for example, I want to have the colors and the PDB name pre-populated. So I'm just going to provide some colors here. These are all in hex notation like this. And then I can say, okay, these are the inputs that these should be mapped to. So here I'm just going to use the PDB ID, then use helix loop. And the outputs, again, should be our HTML component. And we want the run function to be run if this is happening. So I save this again, wait for the app to rebuild, and reload it. And then I have this example thing down here. So I click on it, and then it will automatically pre-populate all of the examples. And if I click on run again, I have again the app working. So, and that's basically it. So I just save this again. I exit out of the live reloading, And you can see this is just a repository. So I just do git add apply and requirements. Now say I'll commit this. That's radio app. And it will be pushed. Then I will have to sign into Hugging Face to upload it. Let's quickly do this. Yes, so now I will push the changes to Hugging Face. And if I switch back to the website I just showed you, find it. Go back to my website. I should be seeing the website. So this is, you see it says building now. So your files have been pushed to the space. You see here the app py that we just created with all the code that we just had. You can also edit it here from the web interface. And the app should be building and should be ready in a few seconds. Yes. And just to show you, so if the app is running and you have here this logs tab, so you can see what if there's any errors or something is going wrong, then you can access these things from here. And there's also this community function, so if people have questions or if they want to submit some changes to the app, they can very easily do this. And you see now the app is running. This is just the stuff that I showed you locally. So now I can click here, I can click on run, and the same thing is happening. I just put this in the chat. So if you want to convince yourself that it's working, you can also quickly try it. Like this. Okay, just let me quickly jump back to my presentation, and then we can also do questions. Okay, so before we finish the presentation, maybe just quickly a few maybe common or frequently asked questions. So you've seen me install requirements using these requirements files. So what if you have something more complex? So it's like often if you have conda packages, for example, it might be something that has more dependencies that you can't install using pip. If you have the need to do this, then you can either launch a Docker space, as I showed you, that's also possible. You can see if the program you're trying to install or a subprogram within it is available from pip, or if you can also use apt-get to install it. Also, if your app is not just a Python program, but if you call other stuff, so it's just a normal Python application, so you can do everything that you also can do from within a Python script, just subprocess call external programs. That's no problem. If you have an app that uses a lot of resources, for example, this AlphaFold app, that was a little bit difficult to get to run on this shared resource because I had some memory management problems. I really found this Rail library quite helpful to manage this. So basically, it also containerizes part of your Python application in containers that are then, so the memory is deleted after the app has run. Maybe you also want to you say, okay, I love GitHub, I don't want to go to a different platform, then you can use GitHub and just there's an action to sync your GitHub repo to Hugging Face, so then you can have your space running on Hugging Face, but you can still develop on GitHub as you want. Also, as you've seen in this app, basically your run function that will produce one output and then it's finished. And sometimes you want to have sequential outputs, right? So your model will run for some time and generate outputs. If you want to do this, then you can just use a generator instead of just returning a value, and then your model will continue to, or your app will continue to listen for outputs from the model and display them to the user. If you have very large files, because you might know that in GitHub or in the Git repository, you can only have a certain number of file size, then Hugging Face also offers to use Git LFS. So if you have big model weights that you want to put in your space or something else, you can do that using LFS. With this, thanks for listening. I hope I wasn't too fast, but since all the code is available, I think you can just tinker with it. I'm very happy to answer any questions now, or if you want to play with it yourself and then talk to me later, you can also do it. You can reach me on Twitter, or you can on Mastodon, and you can also write me an email. And here's a list of resources to get you started. So for example, I wrote this guide on custom iframes. So if you're interested in how to do this, you can just click here. There's a short description of what I just showed you. There's also a similar kind of walkthrough for a Streamlit app. So this might also be interesting if you want to use a Streamlit. If you have questions on Gradio or Hugging Face stuff, then they also have a Discord app where there's a lot of really helpful people. So if you want to do something and you don't know how to do it, then that might also be a good place to get started. Also, again, want to highlight this platform that I made to kind of share such models. So at the moment, there is no good aggregator specifically for stuff in our field. So if you have, if you develop something yourself, you see something cool, and you can just share it. It really takes a minute max. And the live demo of the model that I just put online, you can also access it here from this link. And with this, thanks, and I'd be happy to take any questions.